Welcome back to ECE 220. Your homework is due today. If you haven't yet turned it in, you can hold on to it if you want. You can remain in your seats, and as I make my way through the audience later today, maybe you can get my attention and hand me your paper. We could hand those to the aisle sections of the class. That's fine, and then we'll collect those. And if I fail to get around to your location during class, if I don't come up with the microphone and ask you a question during class, now everybody's nervous, I'll make sure you bring them forward at the end of class and I get your completed homework on your P-Spice. Make sure your name is on each paper, and if you don't have them stapled, just make sure that you put your name on every paper that you turn in. You don't need to staple or fold the corners. They lie flat a little bit better without folding and bending. We have 2 sections remaining for the orientation lab, Lab 0. And that's today. Friday's section, which I believe is section H, is that correct? And section I is next Tuesday. Are the labs going okay? I might show up today, so if you're in section H, don't get too worked up when I show up. But I do have closed-toed shoes on, and I do have a cat card, but I may not submit mine to the stockroom window. But you do need to do that to report to lab, and make sure you bring something to take notes with. Homeworks 3 and 4 are scheduled. 4 is not yet available, but 3 is available, and you need to be getting that ready to be submitted by the 17th, which is next Tuesday. And exam number 1, I've had questions about calculators. It's pretty much everything but a laptop computer is what you are allowed. You are allowed a TI-83, 84, 89, Inspire, etc., or an HP 50. If you have a question, you can ask me, and we can make sure and get that cleared up or clarified prior to exam number 1. What I want to do now is continue to develop your skills with node voltage analysis, and we'll do that by first looking at different scenarios you might be confronted with when you're applying the node voltage analysis process. Oh, how do I find that current when this is between these 2 nodes? That's the first part of today. How do you calculate branch currents? Then we'll go through a couple of examples. I will actually have you work example number 3 and see how well that goes. Then we will go through more examples after we look at a situation that tries to illustrate why it doesn't really matter how you select the reference node. As long as you get all of the essential nodes identified and you start now referring voltages, node voltages, relative to the reference node you select, you should be able to obtain all the information you need for that circuit. You'll be able to say, oh, this element is absorbing this much power. Well, maybe your V's are not the same as someone else's, but they should get exactly the same amount of power being absorbed with that element. The results should be consistent, even though the voltages, as you have them labeled, may be completely different. Here is the setup for the first part, and that is, how do we find I, this current flowing from node A to node B, in a complicated circuit, but we will now just isolate our attention on what's in this dashed box called C below. Something's going to be appearing, different cases, different scenarios, in that box, and this is to try to help us become more comfortable or to get experience with determining how do we determine I. If we were writing KCL equations at node A and node B, and boom, we're presented with something that's in this box, how do we find I that's associated with what's inside that box? That's the idea. You should be able to see that according to node A, or at location A, if we started calculating KCL, there's a current going to the left through R sub 3, and that would be V sub A minus capital V divided by R sub 3. That would be the current going to the left. The current going down through resistor R4 would be, well, it depends on what's labeled, and I guess I should have said I need to know in that last example that I just spoke about, I was sort of by default assuming this was my reference node. If that hadn't been, I forgot about that R5 down there. If that hadn't been, then I would have to actually account for that in determining what's the voltage there. So we're not going to get into that. What we will get into now is expanding on what's happening inside the box. And this is now the C below. We want to know how do we identify or determine or find this current I going from left to right between nodes A and B. Here's the first one. How do we find I if we know this information relative to what's inside the box? This is now, you've opened up your gift, you've gotten your box, and now you open it up and you now see resistor 7 and 8 connected in this manner between nodes A and B. Your task is now to identify I, or to be able to write an expression that describes I in terms of the given information. And this one should be fairly straightforward. Here we're just applying, I shouldn't say just applying, because Ohm's law is important. We are applying Ohm's law. We need to now, if we want I being directed from left to right, then we need to know what's the potential difference, or what's the voltage dropped between node A and node B in terms of these labels. And that's V sub A, which is where I'm starting, minus where I'm going, which is V sub B. That's the difference, or the drop in potential across those two nodes, and I divide by the series combination of R sub 7 and R sub 8. R sub 7 plus R sub 8. I in this particular box is now V sub A minus V sub B over R7 plus R sub 8. That you should be very comfortable with knowing or doing. That's Ohm's law, writing KCL, or as a component of writing KCL at node A for the current I going to the right. Here's our second gift. We've opened up our box, and now we're presented with this. Here is what's happening between nodes A and B and influencing I. How would you find I in this situation? Do you know I with that current source? I'm sorry, with that voltage source? Can you determine what's happening with I based on that source? Yes.
Well, the total voltage across everything is VA minus VB, and you know that you're going to have additional, I guess, dissipation power at that independent supply there, so you can basically subtract that from the VA minus VB.
Did everybody get that logic or hear that logic? I'm sure it was not picked up on my microphone, but we really are interested still in the drop across A and B, but that dependent source is influencing that drop. And in particular, if we knew the current going through R7, don't we know that that's I? The current through R7 is I. Well, here's what I would maybe do. I would say, you know what? They're trying to make this a little bit more challenging than what I would like. So let me just put that intermediate variable in there. And now I know I is going to be V sub x minus V sub b over R7. There's Ohm's law. And now you're going, yeah, but you just inserted a new variable. How can you do that? Well, you can do what you want as long as it's valid. And it's valid. We just now have to figure out what is V sub x, or can we find V sub x from the given information that we have here. And you might just say, well, I know this point is at V sub a. You might just draw another picture. Here is that dependent voltage source. And we're assuming that we know I sub x from somewhere else in the circuit. In the circuit, I sub x was there, so we would have to know that relative to this dependent source. And then we get over to what we are labeling V sub x, and we could say that that's relative to the reference node, which is the same node that we're using for V sub a. So V sub a, boy, I have too many dashes here. I can't even keep track of what's what. There's our reference node. V sub x is here. V sub a is between that black common negative terminal and the plus at terminal A. Now can we write a KVL equation with this information? Now we can actually think about going a KVL there through that dependent source down through V sub x and back to that location. Pardon? What are the black dashes representing? The black dashes are supposed to be representing the common reference node that V sub a and V sub x are with respect to. Those are now your black lead in the lab that you're connecting to the common, the reference node. That's what I've highlighted or tried to highlight in red. This is now the reference node. And relative to that, now I have another dashed path that's indicating the KVL path that I want to use to rewrite V sub x into these known variables or these known expressions. KVL now from this now says it's minus V sub a plus 0.4 I sub x plus V sub x is equal to 0. Or that now says V sub x is V sub a minus 0.4 I sub x. And that's what was stated in the response earlier. You said you had some drop on the right-hand side of that dependent voltage source that you needed to accommodate when you were determining I. Or I now is equal to V sub A minus 0.4 I sub x minus V sub B over R7. And that's now a valid expression for I in terms of the unknowns in our circuit, V sub A, V sub B, and that dependent current I sub x. Wow, that's kind of a mess, but hopefully you remember the logic to connect that mess. We started out with just saying, let's just introduce a new node, temporary node, I'm going to call V sub x, because then I can use Ohm's law to find I. Then I had to do a little bit of bookkeeping on the side to try to determine what is that V sub x, and that required a KVL equation. That was needed so that I could now remove that intermediate variable V sub x that I was wanting. And now you can say, oh, that's maybe logical. I had V sub A, and what do? I experience a voltage drop to that location, which I labeled V sub x. So now that V sub x minus V sub B over R sub 7 is what I need for that particular box example for this circuit. What if we now were presented with the following gift in that box? Here is something new between nodes A and B. Now we have a resistor. We have a dependent current source that's a current-dependent current source. And we have an independent voltage source. How do we find I in this scenario? Question? So now the answer that was proposed is, could we just find the current with neglecting the dependent source and then take that away when we get that current? Not quite, but it could be thought of, but now that you're making it more difficult than it needs to be. So now in this case, what do we know I to be? Isn't it just the opposite of the dependent current source that says here's the current going between these two nodes, and it's going this way. It's going from right to left. And I wanted the current from left to right. Well, those are just the negative of each other. So it's really saying I is minus 0.5 I sub x. That's all I need. I will obviously need to find I sub x, but that's part of this dependent nature of that dependent source. In this case, I is as straightforward as just saying minus 0.5 I sub x. One of the things that you can't do here is, do you know what, how did I label it? Do you know what this is? The voltage dropped across that current source? No. So that's an unknown, and we If we knew that, then we could find out what the voltage is to the right of R7, and then we would have an expression. But we can't do that because that dependent source is giving whatever current is necessary based on I sub x. And so all we can say, if we want that red current I going from left to right, is that I is equal to minus 0.5 I sub x, the negative of what's being supplied by that dependent current source. This, in fact, is an unknown voltage that is across the dependent source. And that voltage is going to be whatever it needs to be in order to keep 1/2 I sub x going from right to left in that branch. That's by the nature of the dependent current source. And you didn't think you were getting any gifts today. Look at all these boxes we're opening. I don't want this many presents today. Right? Well, we're on the fourth one. We have some more. What is the current I from left to right in this scenario? And here, what you need to go back to is the information or the knowledge you have about independent sources. Here you have an independent voltage source connecting those two nodes, nodes A and B. What do you know about independent voltage sources? What do they do? I don't know, you just turn them on and adjust them. And what is in that process of adjusting? It's always going to be that 9-volt battery, isn't it, between A and B? It's going to maintain 9 volts no matter what. I didn't like that. My screen just seemed to do a little something weird. Let me check and hope that it's still recording. Who knows? You can report back to me if I've now been lost now that I'm telling you to report and it's not even being recorded. Anyway. That's in the other box. We'll have another. All right, getting back to this. What's the voltage source? So that tells me maybe I shouldn't be walking around too much in the classroom. Maybe. Did you guys see this screen or is it my eyes? I thought it kind of flicked a little. I'm a little nervous when I'm recording. What we're going to have to do here is that I is going to be whatever it needs to be in order to maintain 9 volts between A and B. We can't tell given this information. So, because we can't tell that, we're going to have to put that inside what's called a supernode. We'll just circle that entire combination and say, here's a supernode, and now we want to write a KCL equation relative to what's happening to that supernode. We'll need to use a supernode, and that supernode is defined by that red dashed enclosure, and that enclosure, we can apply KCL to any closed, what do I want to say, any encirclement of a circuit network. And here we're simply encircling V sub A and V sub B in that branch. We'll need to use a supernode, which we'll learn about a little bit later. But we can find a connection between that node A and node B's voltage. There is a constraint equation that we could write if we need it. We now have a connection between V sub A and V sub B. V sub A is relative to our reference node, and we would go from our reference node up to V sub A, so that's now a voltage rise. That's a negative drop if you're keeping track of drops. That's now minus V sub A. We have another negative drop of minus 9, and then we have a drop from V sub B back to the reference. And so now we actually have minus V sub A plus V sub B will always be 9. And that's a constraint on V sub A and V sub B because we've inserted this independent source between those two nodes. We just have to live with that. And we'll figure out what the other currents are in that circuit based on applying KCL to this supernode that we've now used to enclose this constraint that we can't really deal with other than to say V sub B minus V sub A is always 9. That constraint we have to use in solving the circuit. All right, you're getting tired of gifts. This is the last one. What is I here? This looks very similar to what we just talked about, does it not? Except now somebody has actually given us V sub A. Now they've told us V sub capital A is minus 4 volts. So let's write another constraint equation. We really can't tell I yet from this. So our constraint equation is from KVL. And now we know that we have minus V sub A plus 10 plus V sub B is equal to 0. Or V sub B is now V sub A minus 10. But V sub A was in fact minus 4. So now we know V sub B as well as V sub A. It's 10 volts lower than minus 4. It's because it's 10 volts dropped from minus 4 to V sub B. That's a voltage drop. In order to figure out I, we could apply KCL at either node A or B to find it. But now, given this information, we know V sub A and V sub B. If we want I, we can write a KCL equation. In our earlier circuit, this was extracted, this was in the box in our earlier circuit. Let's see how well you do with applying node voltage analysis to this circuit. Let me give you a few minutes to solve this circuit. And since this is not an exam, you can discuss it with someone near you if you want. Thanks. Did everybody finish? Did you get started? What was your first step in this process of solving this equation or this circuit? Did you look for essential nodes? Did you find, not sure what color I am, did you pick that one to be your reference node? Probably. That has a lot of elements connected to it. That's typically where we assign our reference node. Is this an essential node? And is this? How many node voltages did you identify? How many essential nodes do you have? You have 3 essential nodes. One of those is going to be referred to as the reference node. So we have 2 possible node voltages. We could say here is V1 and here is V sub 2 if we've now made that our reference node. What do we know about V1? It's given, isn't it not? It's fixed because it's determined by that voltage source of 10 volts. You needed to calculate one node voltage in this circuit, and that's V sub 2. I'll let you do that. Let me just tell you that V sub 2 is 10.8 volts. Let's assume that you know, no assumption whatsoever. You do that on your own at home. Verify that that's in fact the case based on what we've done. So you have all this room to do that. Example 4. In this particular circuit, now we have some dependent sources, all depending on the voltage dropped across that 3 ohm resistor. What if we now wanted to find all of the powers associated with those individual elements? We want to know what power is associated with the dependent voltage source, with the independent voltage source, with the 6 ohm resistor. How do we attack this problem? How many essential nodes do we have? Are there supposed to be two V1s up here? Good question. Did Tharp have a breakdown or what? That is actually what I want. So now we have two different dependent sources. One's a voltage source and one's a current source, and they're both V1. So the units of V1 on one side are going to have to be amps. V1 on the other is going to have to be units of volts. And V1 is this voltage dropped across the 3 ohm resistor. So we have a variable in our circuit that other sources depend on. We have two dependent sources and we have an independent voltage source. And we want to now figure out what are all the powers on each of these individual elements. What do we need in order to solve that? If I handed you, now I give you another box, and it contains V1, could you do what we need for this circuit? If I happen to just give you V1, could you tell me what power is associated with that 3 ohm resistor? Could you tell me the power of that dependent current source on the right? If I said V1 is this, yeah, now you know the voltage and the current associated with that. You know the voltage and the resistance of the other. You would know everything if we could find V1. Let's find V1. V1 is actually one of our dependent, let me just say, one of our node voltages. Here is an essential node. Here is an essential node. Are there any other essential nodes in that circuit? And if we label this one as our common, now V1 is our node voltage that we need to find. The node voltage is V sub 1, which is going to be determined by the voltage dropped across that 3 ohm resistor. Whoops, I forgot to give you all the information. No. So, what is that current? Can we find it? Well, if we can't, if we knew it, we could now write KCL at that node voltage that we need, right? If we now wrote, if this is now step 2, and we say, let's write the KCL equation at node 1, that's I sub L plus the current going down here plus the other current in the dependent source, V sub 1. KCL now says that I sub L plus V1 over 3 plus V1 is equal to 0. Are we okay with that expression? But we introduced another variable, I sub L. We need to find that. And we can find that by hopefully maybe another formula, which could be a KVL around that leftmost mesh. Because I sub L is in that loop. Let's now find or see if KVL is helpful to find I sub L. Can you now write a KVL around there? Going up through that dependent voltage source is minus V1. In terms of I sub L, what's Ohm's law associated with that 6 ohm resistor? Moving in this clockwise KVL direction. I'm minus V1 going up from the lower left-hand corner. Then I want to go through that 6 ohm resistor from left to right. What's Ohm's law tell me that voltage is in terms of 6 and I sub L? It's minus 6 I sub L plus 12 plus V1. The KVL to find I sub L is now whatever we just said, minus V1 minus 6 I sub L plus 12 plus V1 is equal to 0. Well, that was convenient with the V's, V1s, minus V1 plus V1. This leads to minus 6 I sub L plus 12 is equal to 0. Or I sub L is equal to 2. If I sub L is equal to 2, do you see that now can be used in this equation to allow us to solve for V1? Question? Now it should be, what was the question? Since I drew KVL opposite to I sub L, you want I sub L to be the negative of what I calculated? Do I? So now we just have to live with the polarities or the labels that we have introduced. I arbitrarily introduced I sub L going from right to left, and in writing my KVL I had to go opposite or opposing that, and so I've already accounted for that negative sign in my KVL equation using Ohm's law. So I now said minus V1 minus 6 I sub L. If I had defined another current, let's say I associated with KVL, that red KVL, I could have said minus V1 plus 6I plus 12 plus V1. I would solve for I, and then that would be the negative of I sub L. Now are we okay? Those, you need to be comfortable with that confusion in your head as you're working through this. And you don't want to make it that, you don't want to confuse yourself too much, but you want to be able to clarify everything. Now what I'm wanting to do is use this in the first equation to be able to write 2 plus V1 over 3 plus V1 is equal to 0. Or if I multiply everything by 3, I have 6 plus V1 plus 3V1 is equal to 0. What did I say? Multiply by 3? I wanted to say multiply by 3. Did I say that or did I say 6? 3? Okay. It's Friday. 5 more minutes, really. That's all. I know you're watching the time. We now have this. 6 plus 4, and my 6 is partially there. V1 is now minus 1.5 volts. That's V1. Now, what was my ultimate goal? I wanted to find the powers of all of these elements. Is it okay if I say here's element A, here's element B, here's element C, here's element D, and here's element E? And I want to find the powers of all of those. The power of A. What is the power of A using or applying the passive sign convention? And let's use I sub L. Since it's there and we have it, what is the power of A using the passive sign convention in terms of the voltage of that dependent source and the current? What's the passive sign convention going to be? What's the voltage that we're going to use? V1. What's the current? We said I sub L. Passive sign convention, which way is that current going relative to the labeling on that element? It's going into the plus sign before it goes through the element. It's going to be positive. It's going to absorb whatever the result is, but we now have, with the passive sign convention, V1 times I sub L for our power of A. This is now, with the passive sign convention, V1 times I sub L with a plus sign. And this was now minus 3/2. That was V1, and I sub L was 2. We now have minus 3 watts absorbed. Or we could say we had 3 watts supplied, or 3 watts developed, because it's a minus 3 absorbed. What about B? B is the 6 ohm resistor. What do we know about that? What's its power? Could we find, do I have V anywhere else on that diagram? If I said there's our voltage, V, positive, negative, right to left, passive sign convention tells us what's my sign here, plus or minus? Plus, isn't it? But V is just R times I sub L. And what was the resistor? 6. And I sub L? 2. Power of B? That makes sense. It's absorbed 24 watts. What about C? What's the power of C with the passive sign convention? If we're using I sub L, isn't it negative? So now we have P sub C is minus the 12 times I sub L. And this is minus 12 times 2. This is now minus 24 watts absorbed. It's actually supplying power. It's supplying what that resistor needed, the 6 ohm. What about D? Passive sign convention. It's a resistor. Isn't it I squared R? Or it's V sub 1 squared over R. What about E? That's the current V1 times the voltage V1. And what's the passive sign convention for that? Positive. If the result comes out negative, we know it's actually supplying. I'll do that after we stop, but you can check your work, which I hope you do, over the weekend. Enjoy your weekend. Make sure I get your homework for PSpice turned in before you disappear.